Okay.
Okay, welcome everyone to HO Colloquium today by our very familiar Juan Manuel Boraro. Um, it is my great pleasure to introduce Juan. Juan did his PhD in 2004 at the University of Göttingen, Germany. He is under the supervision of Sami Solanki and Franz Neer. He was a postdoc and project scientist during 2004 to 2008 at HAO, working on the HMI instrument and VFISV inversion code with Steve Domzik, Amy Norton et al. And during 2008 to 2010, he took a tenure track position at Max Planck Institute for Solar System Research in Göttingen, Germany. Then, from 2010 onwards, he is a staff scientist at the Institute of Solar Physics, former Kiepenheuer Institute in Freiburg, Germany. Today, Juan will be speaking on the role of the Lorentz force in sunspot equilibrium. Juan.
Thank you, Naosumi. Thank you also for inviting me to give this talk about our latest work. It's a pleasure to be here. I see so many familiar faces. I feel a rush of emotion when I see so many people I know and such a fond memories that I have from HAO that it makes me a little bit emotional, honestly. Yeah. So, like I said, it's a pleasure to be here and to present this work that I have done partly in collaboration with some people at HAO, as you can see from the author list, in this case from Matthias Rempel. And as you can see, the title of the talk is the role of the Lorentz force, and in particular, its fluctuations in the equilibrium of sunspots. I have a couple of disclaimers to do before we start. Number one is that the presentation has actually quite a limited amount of slides. I think I have only 20 slides, but some of them are extremely dense. So I would like to go through some of them patiently and slowly, so we can follow the reasoning, right? The second disclaimer is that it's past 10 p.m. here in Germany, so I'm not wearing black tie. I'm almost on my PJs, so excuse my informality, but it is what it is. All right, so let's get started. With a little bit of motivation as to why we are doing this work. And like everyone knows in the audience, probably, sunspots are known to present a large variety of dynamic phenomena. And many of these dynamic phenomena, I have a typo there, I just realized, occurs at very small scales. And these can be things like the average flow, running penumbral waves, moving magnetic features, umbral dots, penumbral gains. And typically, these phenomena evolves in short time scales of minutes, sometimes tens or dozens of minutes. Now, on the other hand, sunspots, along with structures such as filaments or coronal holes, are one of the longest-lived structures on the solar surface. They survive for days and months on there. So it has to be that the overall structure must be very close to some sort of equilibrium, or that they evolve rather slowly through quasi-equilibrium states. Now, from a theoretical point of view, the equilibrium of sunspots has been intensively studied by people like B.C. Lowe and Pizzo, who are well known to everyone at HAO. but these theoretical studies were necessarily simplified. They employed self-similar solutions of the magnetic field, or they employed actually symmetric solutions, and therefore they could only address the equilibrium on the radial and on the vertical direction. Now, why is this important? This is important because actually from spectropolarimetric observations done for several years, as you can see already, we do know that the variations of the magnetic field along the radial direction and the vertical direction are actually rather small, of the order of less than 1 Gauss per kilometer. If we compare those variations with the variations of the magnetic field along the azimuthal direction, which I have there as 1/r dV phi, those variations are almost 1 order of magnitude larger than the variations along the radial direction. So this essentially means that we've been missing this very important ingredient in the study of sunspot equilibrium. The phi direction has been ignored, despite being the most relevant one. So our goal with this work was actually to address how is a possible equilibrium along the azimuthal direction maintained in sunspots. Now, in order to do that, we are going to be using today a variety of tools. Some of them come from observations and some of them come from simulations. In fact, we are going to be using 2 sets of observations, one of them from Gregor with a GRIS instrument. This is a ground-based telescope here on the left side. We are going to be using here on the middle, we are going to be using data from a spacecraft, the Ionosphere spectropolarimeter. And on the right side, you see a numerical simulation, an MHD simulation of sunspots produced by Matthias Rempel and Markus Maschmann. And the goal is to compare these 3. Now, for Gregor and Ionosphere, the comparison is relatively straightforward because even though Ionosphere telescope has a primary mirror which is about 3 times smaller than Gregor, it also operates as a wavelength which is about 3 times smaller. Therefore, the effective spatial resolution in Ionosphere and in Gregor observations is essentially the same. Now, for the MHD simulation, the situation becomes a little bit more complicated because the original resolution of the simulations is much better than those of the observations. So somehow we need to find a common scale to compare all these 3 things. And the way we are going to be doing it is we are going to try to improve the observations, and we are going to try to worsen the simulations in a way. So we are going to try to bring down or improve the resolution of the observations, and we are going to degrade the resolution of the simulations. And an example of this, you can see it already in each of these panels. Each of these panels is divided in 2. There is a left side and a right side. On the left side is the original data, the one that was taken either by the telescope or produced by the simulation. And on the right side, for Gregor and for GRIS, what you see is the improved data employing the PSF of those telescopes. So you can see that from the left to the right, the situation here improves, and from the left to the right here, the situation improves. Now, for the simulations, it's exactly the opposite. From the left to the right, the situation worsens, because what we have done is to degrade the quality of the simulations to something which is more comparable to the observations. And now what we are going to do is take all the right panels in these 3 figures, that they have approximately the same resolution, and compare the properties of the magnetic field, of the plasma flows, of the pressure, of the temperature, and this kind of thing. All right, so from the simulations, it's relatively easy to do because they provide already data cubes with all these physical quantities, the 3 components of the magnetic field, the 3 components of the velocity, and so forth. But for the observations, it's slightly different. Our data is not the actual physical parameters, but are comprised by the observations of the Stokes vector. And now the question is that we need to take the observations taken with Gregor and Inode and transform that into physical parameters. And the way we do that is, of course, through spectropolarimetric inversions. In this case, we use the Firth code. Now, I feel like I'm preaching to the choir here when I talk about the spectropolarimetric inversions, because everyone at HAO and also there at NSO, I see the little window, know about what these things are. But our inversion code has some particular features that I think they are worth mentioning. Number one is that in general, the spectropolarimetric inversions transform observations of the Stokes vector on the solar surface as a function of wavelength into the physical parameters in the solar atmosphere as a function of xy, which is the solar surface, and as a function of the optical depth. This is typically what an inversion code does. But the Firth code works a little bit different. It actually works directly on the Z scale. Therefore, we do not convert from the Stokes vector to T of xy tau. Instead, we convert from the Stokes vector as a, and from the Stokes vector to the temperature as a function of xyz, the magnetic field vector as a function of xyz, and so forth. And how can we do this? We can do this because the gas pressure that Firth uses does not assume hydrostatic equilibrium. Instead, it considers magnetohydrostatic equilibrium. And because of that, the gas pressure is much more reliable. And through that, we can convert easily between the optical depth tau and the vertical coordinate along the line of sight. So that's something that I believe Firth is the only code capable of doing that at the moment. Now, another feature that Firth has, and we will be using today, is that it can consider, during the inversion, the PSF, the instrumental PSF of the telescope. This was a method originally developed by Michiel van Noort, but that he has been also adapted into our inversion code. Now, other features that I think they are worth mentioning, even though we are not using them today. That's why they have this red tick mark here. The green ones, we are using them today. The red ones are implemented, but we are not using them today. Is that Firth is an inversion code that actually can guarantee that the magnetic field that it retrieves is actually divergence-free. Not a lot of inversion codes can do that either. And in addition to this, it can impose some sort of regularization, Tikhonov regularization in our case, along the vertical and the horizontal dimensions in order to increase the smoothness of the solutions. So now, before we proceed any further with the actual results of our work, I would like to get into two of these points, which is the MHS equilibrium and the PSF coupled inversion. If we go to the first one, the MHS equilibrium within the Firth code, we see that basically what we are doing is to solve for divergence of P being balanced with the gravity force plus the Lorentz force, where the Lorentz force is obviously this is correct. No, this is incorrect. Is this correct or is this incorrect? It's J cross B. No, this is missing here, and there should be a cross B on the other side. I'm sorry, that formula is not right. At any rate, even though this equation is the one that establishes the magnetohydrostatic equilibrium, this is not actually the equation that Firth is solving. Firth solves a slightly modified equation that we obtain by first removing the density from here using the equation of state. Then we divide this whole equation by the gas pressure, and then we take the divergence on both sides. And what we go is from a linear system of first order partial differential equation to a single second order partial differential equation, which looks like a Poisson equation. Now, This equation, how do we solve it? Okay, well, we can solve it because the temperature and the magnetic field are given by the inversion. So this term here on the right side can be fixed by the Stokes inversion. And part of this term, in particular, the one of the Lorentz force, is also fixed by the Stokes inversion because we know the magnetic field. Unfortunately, we have the gas pressure here and here. So we have to solve this iteratively. The way we do this is using the Fishback package, which was actually developed at NCAR in the mid-70s, if I remember correctly, and for which I'm very grateful to Matthias and Juhon Fan for introducing me to this package. So the way we do it is we start with some guess for the gas pressure. We know the right-hand side, and using some boundary conditions, we solve for the gas pressure again. And whatever gas pressure comes from here, we plug it back into the right-hand side, and we keep solving until it converges. And then we have a magnetohydrostatic gas pressure instead of hydrostatic gas pressure. Now, the whole point here is that the temperature that comes from the inversion, together with the magnetic field that comes from the inversion, and the boundary conditions in the gas pressure that we obtain to solve this equation are not always consistent. In fact, it cannot be guaranteed that they are consistent with each other. Therefore, the above equation, this equation that satisfies MHA's equilibrium, is not strictly verified in all cases. One should see it more as being fulfilled in a least square sense along each of the spatial directions. So the final solution of the gas pressure does not satisfy the strictly magnetohydrostatic equilibrium, but it deviates from it as little as possible and tries to compensate the deviations along X, Y, and Z. Okay, so now that we have the magnetohydrostatic equilibrium explained, we move into the PSF coupled inversion. The PSF coupled inversion, basically, what it does is that it considers the effect of the point spread function during the inversion. There's no need to deconvolve the data prior to the inversion. It's done internally. And it has a number of advantages. One advantage, very important one, is that it never deconvolves, this method. It only convolves. And we all know that deconvolutions are typically quite prone to instabilities. Convolutions are always much more stable, so they should be the preferred method. The second advantage is that because it convolves every time it produces a synthetic Stokes profile, it actually considers the wavelength dependence of the data, which is not something done during the convolution. When you deconvolve your data, you typically deconvolve the 2D image at each wavelength, and you don't care that actually those wavelengths are connected. Through the coupled inversion, those wavelengths are connected through the actual radiative transfer. Now, the PSS that we are going to use are slightly different for each of the instruments that we are using. Obviously, for Gregor, our PSF is composed by two contributions. Number one is the diffraction limited contribution of the PSF, which is considered to be that of a 1.44 meters primary mirror with a 45 centimeter central obscuration, these spiders. And then, because Gregor is a ground-based telescope, we also add a contribution for the seeing. And the seeing, we assume that is a Gaussian contribution with a sigma of about half an arc second. And it actually contributes to about 43% of the total observed power. Now, for INODE, it's a little bit easier because it's in space, so we can get rid of the contribution by the seeing. So all we need to include is the diffraction limited PSF, which in this case is for a 50 centimeters primary mirror with a 17 centimeters central obscuration and 3 spiders and a slight defocus. Now, these are the PSFs that you see here on the top for Gregor and in the middle for INODE. And of course, here for INODE looks very much like an ideal PSF. And the one in Gregor is obviously much wider because it has a contribution from the Gaussian due to the scene. Now, for the simulations, we do not try to make it too fancy. We assume that it has no central obscuration. So our ideal PSF is actually an ID function, and you see it there. The important thing is that once we consider these PSFs, all three data sets from Gregor, from Inode, and from the simulations, they have an equivalent spatial resolution of about 0.3 arcseconds. So they are already ripe to be compared. We can use the convolved results of the inversions and the convolved results of the simulations and look at them in a leveled playing field. So, as an example of these inversions using the coupled PSF method, you can see here 3 maps where you see on the top panels, you see the temperature, and on the bottom panel, you see the inclination with respect to the vertical of the solar surface, the inclination of the magnetic field with respect to the vertical on the solar surface. Sorry. And you see here for Gregor, for Inode, and for the MHD simulations. And then again, what you have here is on the left side of each of the panels is the results without the coupled PSF inversion. So things look a little bit more blurry, but the moment you include the PSF during the inversion, the quality of the inversion, especially for Inode and for Gregor, dramatically increase. For the simulations, it's exactly the other way around, because we go from a highly resolved structure of the temperature and magnetic field to a worse resolved structure because we're actually degrading the simulation. So now, once we have all this, we have everything necessary to start producing results. And the results that I'm going to be showing right now are essentially, I don't know if you guys can see it very well, but there are these arcs here, white lines here on the penumbra, and one other one in the umbra. Is that visible? Can I get like a yes or no from the audience?
Yes.
Yes.
Okay. So each of those arcs are along an azimuthal cut for a constant radius within the spot. And the outer one is in the penumbra, and the inner one is in the umbra. So now what I'm going to do is to plot different quantities along those arcs. The first quantities that we are going to look at, because this is something that people have looked in the past, so it will help us warm up to the future results, is the correlations between the strength of the magnetic field and the inclination of the magnetic field along our outermost arc phi. Now, this is quite a dense plot, so I'm going to spend a few minutes to explain it, and then the next plots will be more straightforward to follow. Okay, so in the upper panel, what we have is on the horizontal axis, we have the magnetic field strength. And in the vertical axis, we have the inclination with respect to the vertical of the magnetic field. Each point in these scatter plots corresponds to one point along those arcs, okay? And we have 3 different clouds of points. Blue color is for Gregor, red color is for Inode, and black color are for the simulations, okay? Now, what I have here are also linear fits to those cloud of points. And at the bottom, I plot also the correlation coefficients for each of those scatter plots, okay? So the first thing that you can see is that the correlation coefficients are negative, and they are rather large, smaller than minus 0.5, and in some cases very close to minus 0.8. Now, there are 3 little panels at the bottom. Those 3 little panels at the bottom show in purple the magnetic field as a function of phi, so how the magnetic field changes along that azimuthal path, and in green, the inclination of the magnetic field. And then this leftmost panel is for Gregor, the middle panel is for Inode, and the rightmost panel is for the simulations. Okay, so what do we see here? Well, what we see here clearly is that very strong magnetic fields here for the simulations, or here for Inode and Gregor, are more vertical than the more horizontal, that the weaker magnetic fields. So there is a strong anti-correlation. You see that also here. Whenever you have a peak on the inclination of the magnetic field, you have a minima on the strength of the magnetic field. This result should come to no surprise to absolutely no one. This has been known for 30 plus years. It essentially highlights the uncombed structure of the penumbral magnetic fields. What I think it was Stanfield or even Bruce Lights or Andy Skumanish in the early 90s named as spines and intraspines. The spines are horizontal magnetic fields that are relatively weak, and the spines are vertical magnetic fields that are relatively strong in comparison. Okay, so now that we have understood this a little bit crowded plot, I'm going to show similar ones for different physical quantities. The next physical quantity that I wanted to show is correlations of the gas pressure and the inclination. And here, what you can see is that now more vertical magnetic fields have a larger gas pressure. So now we have positive correlations. And the positive correlations are also rather large. They are larger than 0.8, and in the case of the simulations and of Inode, closer to 0.9. And you can see here how that correlation actually is. I'm not making it up. You see that whenever there is a maximum in the gas pressure, whenever there is a maximum in the gas pressure, there is also a maximum in the inclination of the magnetic field. And the last one I wanted to show is the correlation between the density of the plasma and the inclination of the magnetic field. And just like it happens with the gas pressure, the density is positively correlated with the inclination of the magnetic field. Meaning, when the magnetic field is inclined, the density is very large, and when the magnetic field is more vertical, the density is much smaller. Okay, so let's make now a little parenthesis. Let's regroup what we have learned, and let's afterwards move into something even newer than this. So far, what is new and what is not? What is not new, like I already explained before, is that in the penumbra, stronger magnetic fields are more vertical and weaker than more inclined magnetic fields. This is the typical structure spine intraspine, already mentioned by Bruce Lights in early 90s, or was also coined by Solanke and Montalban the same year as the flux tubes and the background. Boy, do I have typos on that paragraph or not? Okay, moving on. Something that was suspected but never proven is that due to total pressure balance considerations, the intraspines that have a weaker magnetic field and a larger inclination should also have larger gas pressure and density. This was, again, a theoretical prediction, but could never be confirmed until now with these observations. And something that is now really, really new is that for the very first time, using inversion codes, we can have access to physical parameters that we could not really consider reliably before, such as the gas pressure and the density. Why? Because it came from hydrostatic equilibrium. Now, because we use magnetohydrostatic equilibrium, these gas pressures and densities are much more reliable. But in addition to this, and this is what we are going to be doing for the next 15 minutes or so, is that we can look at the Lorentz force. The Lorentz force involves spatial derivatives of the magnetic field. And unless you have the magnetic field in the Cartesian coordinates, you cannot calculate those spatial derivatives. You need to have them as a function of x, y, z. If you have them as a function of x, y, tau, you cannot do this. Thanks to our code, we are now in a position that we can determine that. Let's now plot the following. Let's plot here the Lorentz force and the inclination of the magnetic field as a function of the position along the outermost arc in the penumbra. So we see the typical inclined field, vertical field here, horizontal field, vertical field, horizontal field, vertical field. And what we see with the Lorentz force is that the Lorentz force is also oscillating, but doesn't seem to be entirely correlated with the inclination of the magnetic field. It almost looks like as if it was sort of out of phase, right? So if we think in terms of the inclination as a cosine function, maybe the Lorentz force behaves as a sine function. Okay, if that's the case, then maybe the derivative of the Lorentz force or the derivative of the inclination is correlated with the Lorentz force. So that's what we do on the plot on the right. On the plot on the right, we plot the Lorentz force and the derivative of the inclination as we move along phi. And now we see that indeed these two things are extremely positively correlated. Now, I should say the following, which I forgot, which is we are plotting the Lorentz force along the phi direction, okay? Not about x or y or z, but along the direction, tangent to the direction of the arc, okay? And this is what is very strongly correlated with the variation of the inclination. So what we see here then is only for Gregor, but the same thing happens for Inode, which is that the Lorentz force is the largest at the boundary that separates the intraspines from the spines, which is exactly where the inclination changes most rapidly. Okay, that's cool, I suppose. But let me ask you the following question. If the gas pressure correlates with gamma, and the phi component of the Lorentz force correlates with the derivative of gamma with respect to phi, does the phi component of the Lorentz force correlate with the derivative of the gas pressure with respect to phi? Okay, let's look at that. Let's look at the correlation between L phi and dPg d phi, okay? And that's our next plot. We have on the x-axis, we have 1 over r derivative of the gas pressure with respect to phi. And in the y-axis, we have the phi component of the Lorentz force. And here, lo and behold, all those scatter plots become straight lines. You get Gregor, almost a one-to-one straight line. Inode, almost a one-to-one straight line. And the simulations also a one-to-one straight line. The correlation coefficients are 90%, for the simulations, 97%. So, and here you see that these correlations are essentially perfect. The phi component of the Lorentz force almost completely falls on top of the azimuthal variation of the gas pressure. In fact, for the simulations, it's so much that you can basically not see the purple curve anymore. So, two things to say here. Number one is that the correlation is almost 100%, and that the slope of this curve is essentially 1. Okay, so what does this mean? Oh, well, should I jump into this? Yes, we do exactly the same thing now, but instead of for the outermost arc in the penumbra, we do the same thing, but for the innermost arc in the umbra. And again, we see very similar results, which are that the slope of the curves are essentially 1, and the correlations are essentially 90 to 100%. I mean, you can see here the correlation for the MHD simulations. Okay, so if the slope is 1 and the correlation is 100%, it essentially means that 1 over r dp d phi is essentially equals to the phi component of the Lorentz force. And that's the root of a magnetohydrostatic equilibrium. How come? Well, if we take the, and look, here I have the Lorentz force correctly written. if we take the momentum equation in ideal MHD, and we discard the terms related to the velocity, we discard the gravity, because the phi direction is perpendicular to the gravity, so this term plays no role. And we also discard the viscous forces. This is the tensor of the stress tensor. Essentially, what we have is that the gradient of PG is essentially the Lorentz force, and that's exactly what we have here. Therefore, the main result of our study is that both the outermost arc, the penumbra, and the innermost arc, in the umbra, are essentially in almost perfect magnetohydrostatic equilibrium. Now, we have done this for two little paths around the spot, right? Is the entire spot in hydrostatic equilibrium? Can we extend this analysis to the entire spot? Well, yes, we can. Let's do it. Let's look at the correlations between the phi component of the Lorentz force and the phi derivative of the gas pressure and the slope of those scatter plots as a function of the radial distance and as a function of the vertical coordinate. And what we are looking is for those things, for the correlation to be very close to 1 and for the slope to be very close to 1. Only when those two things happen, we can say that that region of the sunspot is in magnetohydrostatic. Okay, so that's our next plot. What you see here is results for Gregor on the left side, results for Inode in the middle panel, and results for the MHD simulations on the right side. On the upper plot, what you have are the correlations between the derivative of the gas pressure, as derivatives with respect to phi, and the phi component of the Lorentz force. And in the bottom panel, what you have is the slope of the linear fit to that scatter plot. Okay? So only when those two things are close to 1, we can say that the magnetohydrostatic equilibrium is fulfilled. So now if we look at Gregor, what we are looking at Gregor is for regions where the correlation is almost 1. Here, very reddish color, all this region here. And we are looking for regions here in the slope that are sort of white color, somewhere around here. Okay? I should say that these two lines, I forgot to say, this black line here is tau equals 1, and the upper black line here is tau 10 to the minus 2. Okay? So the conclusion here is that for Gregor, we are in magnetohydrostatic equilibrium essentially all the way from the umbra up to the middle of the penumbra, and only where the slope is also 1, which is around tau equals 1. We see the white color follows more or less the tau equals 1 curve. A very similar result we obtain for Inode. We see that the correlation is almost 1 from the umbra all the way to the middle of the penumbra, and that the slope is 1, the white color here, also close to the tau equals 1 level. Meaning, if we were to plot or to make this figure, we would get exactly the same in those regions where the correlation and the slope is close to 1. Interestingly, for the simulation, you can see that the correlation is extremely close to 1, almost everywhere, and that the slope is extremely close to 1. I'm not going to say everywhere, but also in about 70% of the sunspot. So the simulations also predict in a way that along the azimuthal direction, essentially, the sunspot is in magnetohydrostatic equilibrium. Now, because the simulations give us a wider range of heights, we can establish that fact that we are in magnetohydrostatic equilibrium for a range of heights of somewhere between minus 100 to 400 kilometers, where 0 is the continuum. Unfortunately, for the observations, we don't have such good sensitivity. We can establish that the sunspot is in magnetohydrostatic equilibrium for the same range of distances, but only in a range of heights of about 100 kilometers around the tau equals 1 level. So now that we have established that the sunspot is in magnetohydrostatic equilibrium, the question is, what's the main ingredient here? What is the main contributor to the Lorentz force? Is it the magnetic tension or is it the magnetic pressure gradient? And to do that, we have this following plot here, which is basically the decomposition of the Lorentz force in those two terms. P stands for the tension, and the gas pressure. G stands for the magnetic pressure gradient. And so we plot these two terms in Gregor, in Inode, and in the MHD simulations, again, as a function of phi. And we see that essentially, in almost all cases, it is the blue contribution, which is the gradient of the magnetic pressure, the one that contributes to the Lorentz force. So not only we can say that the sunspot is in magnetohydrostatic equilibrium, we can say that it's also thanks to the magnetic pressure gradient instead of to the magnetic tension. And well, now I come to my conclusions. Conclusions is that we have obtained, at least observationally, theoretically or from the simulations is a different question, but at least observationally, we can now determine physical parameters like the temperature, the velocity, the magnetic field, as a function of the three Cartesian coordinates instead of a function of the optical depth. In addition to this, we can determine physical parameters that we had no access to before. For instance, before we could not rely on the density or on the gas pressure, or for that matter, the electric currents or the Lorentz force that came from hydrostatic equilibrium. Now, indeed, we can. And through this new technique, applying it to the penumbra, we have learned something new, that the intraspines have larger gas pressure and density than the spines. We have learned also that the Lorentz force is the largest at the interface between spines and intraspines, where indeed the inclination changes the most. We have also learned that the largest contribution to the Lorentz force along the fine direction is the gradient in the magnetic pressure. We have found extremely high correlation between the changes in the gas pressure and the Lorentz force, which essentially means that in the phi direction, advection plays no role, viscosity plays no role, and time dependence plays no role in the force balance equation. And we have confirmed all these results with two sunspots, observed at two different wavelengths, with two different instruments, one on Earth, one around the Earth, and on top of that, we had added the results of MHD simulation. And the main results is that along the azimuthal direction, sunspots are essentially in magnetohydrostatic equilibrium, which, in a way, helps to understand why they last for so long on the solar surface. And having said that, come to the end of my talk, and I'll take any questions that you might have. Thank you.
Thank you. So, questions? From the room, anyone from online?
There was one on the
Change.
Oh, no, that was a clap. Oh, maybe they were clapping. I have a question.
Yes, please. Hi, Juan. Nice
Hi,
talk.
Johan. How are you?
Just wondering, I was, you in the procedure for the inversion, you get the pressure, it's not from inversion, the pressure is from solving the hydrostatic balance, not in a magnetic MH hydrostatic. So don't you expect it to satisfy all the force balance? I'm just saying it's PG determined from solving the Poissonic equation, from the inverted J, inverted B, inverted temperature, inverted stuff. Oh, you have temperature as well. So you get Okay, you invert density? No. I'm just saying
No.
it's
The density comes once you get the gas pressure and you get the gas pressure from the MHS equilibrium and the temperature from the inversion, and you combine those two to get the density through the equation of state.
okay.
Yes.
So don't if you
Your question is actually it's a tricky question. Yeah. Yes and no. So yes, in principle, we try to impose a magnetohydrostatic equilibrium in order to get the gas pressure and the densities. So is it magic then that we get magnetohydrostatic equilibrium at the end?
I'm just trying to understand the procedure of the inversion. So that is a derived quantity. The PG is a derived quantity.
PG is a derived quantity, and it is derived from solving that equation with the constraints imposed by the inversion.
Okay.
Okay?
Okay, so you confirm that it is satisfying the magnetohydrostatic. Yeah, that makes sense. The physics makes sense. Yeah.
Well, yes. Yes, but I take your question a little bit more critically, because it seems to me like you are asking whether this is all a big exercise in circular reasoning.
I'm just saying it.
You're
Yeah,
asking
the
that.
results. Yeah, I mean, the observation can be say, okay, the force doesn't balance. Observation says something, but you won't be able to tell because the PG is derived from the MHS.
Yes.
Oh, I have a follow-up question. But it's like I had like a similar question as Young, but it's basically for the simulation, you have all the quantities, right? Have you also compared like the actual physical quantities in the simulation that are not obtained from the simulation, not from the inversion, but actually from the simulation, to see if you have the same correlations there?
Yes, that has been the right mode, all these right panels throughout my presentation, or the black dots here, the black cloud of points, that's only from the simulation itself.
I see, but it's not an inversion result from the graded observations, the graded, because you showed at the beginning
Yes, that's the simulation degraded to the resolution of the observations.
Okay, but the parameters are obtained from the simulation, not through the inversion.
Correct.
Of this data. Okay,
that is correct.
Thank
yes.
you.
Yeah, I had a question for clarification. You know, the one where you compared the, you just had it up. It was the one where you were comparing both the correlation and the slope for the three cases. But I just wanted to clarify. Yep, that one. What is the y-axis on this? Is this height?
Yes.
You were talking. Okay. And
Yes.
so for the case that you showed originally, were you looking at the slopes? Did they correspond to the tau equals 1 bottom
Yes.
black line?
Yes.
Okay, cool.
Obviously. Yeah.
So good.
If-
I just wanted to make sure I understood that. And then my second question, then it kind of follow up is there any, and maybe this is a question for Matthias, do we have any idea why the simulation is different in the sense that the slope is 1 for all these heights as opposed to just at the tau equals 1, like the others?
I think that was because the observations don't have reliable information when you go far away from tau equal 1, at least with the spectral lines. But
yes, but I think Sarah's question is more, why do the simulations have that? Whether we can infer that from the observations, is a different story. But
yeah, there's two questions there. Yeah. So yeah, why would you expect that for the simulation?
at least in the azimuthal direction, because the strong flows, evershed flows, in the radial direction, right? This is only an analysis of the hydrostatic equilibrium in the azimuthal direction. And there it's pretty well fulfilled. But if you would do the same for the radial direction, then you would have to include the acceleration terms from the evershed flow.
yes.
And even gravity or
I mean, in the radial, there is no gravity, but in the vertical, yes.
vertical direction? I thought you meant to say.
Yes.
Yeah, sorry,
Yeah.
radial
But
So
back
then-
to your first question, from the observational point of view, so in the leftmost and in the middle panels, which are the actual observations, we do not get a very good correlation above tau equals 1 because the amount of information, in particular from the magnetic field, outside of that range is not reliable. We do not get a proper magnetic field, and therefore the calculations of the Lorentz force is basically futile.
Okay.
Inesho.
That would be Kevin.
Please unmute. Please unmute.
Yeah, thanks, Wama. It was great, nostalgic to hear you give a talk again. Can you show where your outer, the two arcs you were showing were, where they are on the sunspot? Okay, so one is the penumbra. So are the azimuthal variations, as they seem very similar between the penumbra and the umbra? Are they similar in amplitude? But also
The azimuthal variations in what physical parameter in particular?
well, you have magnetic field, the inclination and the field strength and so on.
Not really, is it? Let's see. Well, for the for the umbra, I only show the Lorentz force and the gas pressure. I do not show the inclination and the magnetic field. I have those plots, but I just didn't include them in the talk. But in terms of the Lorentz force and the radial variation of the gas pressure, they are actually slightly larger in the umbra than in the penumbra. You see the scale, for instance, on the vertical axis, the Lorentz force goes from -8 10 to the -3 to 8 10 to the -3. That's for the umbra. And for the penumbra, it goes from -5 to 5.
Okay.
Yes.
So it is stronger in the umbra.
It's stronger in the umbra, yes. Indeed it is.
And it looks like the spatial, the size of those fluctuations is smaller. I don't know, it looks like it's on smaller angular scales on the bottom there than in the innermost arc.
Yes. Yes. They change faster. The angular variation is faster in the penumbra. Yeah.
Okay. No, that's neat. Thank you.
Thank.
Other questions?
Oh, KD had a question.
Oh, KD, yes. KD put in the chat. I'm reading KD's question, or can you read one?
I don't see the chat anywhere.
I can read KD's question. We have discussed in the past how to interpret the observations without full spatial resolution, especially in the context of spatial derivatives. How are you handling that here?
Okay. So the way we have handled this is by doing the same analysis on the non-degraded or not PSF corrected data. And in that case, the results stay essentially the same. The amplitudes of those variations change a little bit, but we still get the same correlation coefficient, the same degrees of correlations, and the same slopes for the curves. So if I would have done the same analysis, let me move a little bit some slides, my presentation. If I would have done this analysis using the data on the plots of the left side, which are the ones where nothing has been, no PSF has been applied, we would obtain the same thing.
So there is another question. So you are assuming essentially field factor equal to 1.0 effectively.
Yes.
Thanks. So any other question?
So, but if I may interject, the PSF inversion, what it considers is not that the light that you observe in a pixel might come from two distinct unresolved components within that pixel. The coupled PSF, what it considers is that the light that you see on that pixel is the light that comes from that pixel and the light that comes from the pixels around it. So it's a little bit, conceptually, it's a little bit different.
Other questions? Okay,
Yeah,
can
yeah.
you-
I read you, Katie. I read you. Yeah, yeah. Once you have unresolved structure, the question is in which direction they are unresolved and how then you calculate the derivative. That is a headache and a discussion for probably some drinks.
Okay. Any other questions from the room or on? Oh, Ernesto, Kevin?
No,
It just,
No?
he left it up.
it just left it.
Okay. Okay, then let's thank our speaker again for a very nice speaker.
Thanks, guys. Good to see you all.